How's everyone doing? Yes. All right. Some high. See, I love that. Selena, back in action. You feeling better, Selena? Maybe. Maybe not. All right. Okay. So we're going to talk more about logarithms today. Yes, finally. Okay. Good. Very glad to hear that. I was worried about you. But glad you're doing better. Hope that you continue to be great. Okay. So continuing on with our logarithm stuff, we're going to review our properties today. We're going to talk a little bit about solving equations, and then tomorrow we'll also do a little more solving equations. So I'll probably split this up into 2 days. I don't think we'll do this entire lesson today. We'll shorten it a bit because I don't want it to run for super long. Right? And we have the time. So for question 1, expand the logarithm, right? So that means we want to use our properties that we talked about yesterday to take our logarithm and split it apart as much as possible. All right, we want to use properties to break it down, split it up into many logarithms. All right. First thing I said that we worked on yesterday is when we're doing these problems, first look to see if you can simplify anything. Okay, so for example, I've circled here in the first problem in the green, z to the 12th over z to the 4th. That's something that I can simplify. So before I start using properties, I'm going to simplify that to z to the 8th. Right? And another thing I'm going to do is that 6th root of y, I'm going to write that as an exponent of y to the 1/6. My dog is joining the lesson today. Oh yeah, now we're talking. All right, who else has got their dog with them? This is dog day at the K. Everyone bring their dogs to the lesson. Force your dog to watch college algebra. Nice. What kind of dogs are we talking about? If you got a dog with you right now, you got to hit me with what type of dog is it and the name. Let's go. Cue it up. Dog's scared as hell right now. Yeah, it's been storming like wild. There's some good thunder that's been going on. Well, not good if you're a dog that's scared of thunder, but it's intense. Mini Australian Shepherd named Mocha. Wow, nice. Well, hello, Mocha. Welcome to College Algebra. Nelson, Lab Pitbull Mix. Hello, Nelson. Cheese Chihuahua. I don't know how to spell. Okay, that's fine. Got it. Got that little Chihuahua named Lulu. Her birthday was yesterday. I didn't get her anything for her birthday. Why didn't you tell me? We could have all virtually met up for a birthday party at Chuck E. Cheese or something. You know what I'm saying? A Yorkie and Shih Tzu mix named Iggy. Welcome, Iggy. Welcome, Lulu. All right. These are good. This is an interesting mix of dogs too. You know, usually it's like, well, I've got a golden retriever, a Labrador. You know, which is nothing wrong with those dogs. Those are great dogs. My family has always had golden retrievers. They love golden retrievers. But we got a good mix of various dogs going on here. Chihuahuas, Yorkie Shih Tzu, Lab Pit, Mini Australian Shepherd, Iggy Azalea. You got Iggy Azalea there watching the stream with you, Selena? Damn. Is she trying to sponsor my stream? Today's stream sponsored by the NFL. right? Whenever they're back in action, just make sure you tune in to NFL games. Sponsored by Truman State University soccer program, right? Make sure to get out and head up to Truman State to watch those games. What else? That's mostly it for today. And then Iggy Azalea, if we can get her on board, that would be great. Right, happy to have her. All right, so I simplified the logarithm. I also changed the sixth root of y to y to the 1/6. So there's the same thing. We can write them as a root or as an exponent. Okay, from there, to split it up, again, if you have division, first focus on the division part. So the numerator goes in the first logarithm minus the logarithm of the denominator. Like this. And now I see that there is, maybe I shouldn't use blue highlighter. Right, there's multiplication going on inside the logarithm here. So what I can do is I can take that second logarithm and split that up into two more logarithms. So log base 3 of z to the 8th minus, now remember last time we talked about, we had an example like this. If I have a minus sign before I split something up, put that in parentheses or put that in brackets. Oh my gosh, I just threw my stylus. Log base 3 of x cubed. So when there's multiplication, that gets split up using addition. So log base 3 of x cubed plus log base 3 of y to the 1/6. Super important that we put those two in brackets or parentheses because we have to recognize that that negative sign is going to get distributed to both of the terms. So, equals log base 3 of z to the 8th. Well, actually, let me go ahead and do my next property as well. So remember our last property. Can you see that? Is that bad on the eyes, that purple over the blue? We can take those exponents and move them down in front as coefficients. So 8 log base 3 of z minus 3 log base 3 of x. Also minus, because the negative is distributed, so minus 1/6 log base 3 of y. And there we go. We split it up. We expanded it as much as we could. We used our properties. Okay, we do want to turn that root into a 1/6. That way we can bring that 1/6 out in front as a coefficient. Okay, so if you can, do that. That's the expansion. For number 2, use the change of base to evaluate. So log base 4 of 32. Now, the change of base formula, we can change it to any base. Right? I said most commonly we would use natural log and logarithm. But let me show you another way that this is useful to us sometimes. Right? So if I just try to evaluate this in general, log base 4 of 32, this is basically asking, or this is asking, 4 to what power makes 32? Well, I don't know. Okay. 4 squared, 16. Right, 4 cubed is 64. So somewhere between 2 and 3 is my answer. But what I do notice about 4 and 32 is that they are both powers of 2. So I'm going to actually change this to base 2. So log base 2, remember whatever was inside goes on top. And then log base 2, whatever the original base was, is what goes on bottom. And so, again, like I said, this usually helps us just type it into a calculator easier. But actually, if I have it set up like this, I don't even need a calculator. Right? We can just do this in our heads. 2 to what power gives us 4? Well, 2 squared is 4. So the denominator is 2. And in the numerator, 2 to what power makes 32? Okay, well, maybe you need to think about that for a second or count on your fingers or whatever. Right? So 2 times 2 would be 4. 4 times 2 is 8. 8 times 2 is 16. And 16 times 2 is 32. So that's 5. So 2 to the 5th power makes 32. That's not a 5. So my answer is 5/2. We talked about just mostly using like natural log or common log yesterday. So if you type into your calculator natural log of 32 divided by natural log of 4, it would give you 2.5, which is the same thing as 5/2. It's just the decimal version. But since we love fractions so much more than we love decimals, because we don't love decimals at all, we really like that first answer of 5/2. Such a smooth fraction, perfect. No decimal points needed. Sometimes it's useful to use change of base to change to something that we could just do in our heads without even needing a calculator at all. So it's kind of neat. And I'm looking at the chat. Everyone's saying, yes, I agree. That's so neat. That's so much better. We love fractions. You're the best teacher ever, Mr. Bunnis. So thank you guys for saying that. That means a lot. I appreciate that. Right. So that's kind of a summary that uses all of the properties we talked about yesterday. Right. The first question has all of the expansion or condensing properties, and then the other property that we just didn't mention was the change of base. I agree. That's so neat. We love fractions. Thank you, Mr. Bunnis. See, I knew it. Yeah, I appreciate that. You guys flatter me too much. It means a lot. It means a lot. Right. Did you get that, Lulu? Does it make sense? Iggy on board here. What was the one for Mocha? Mocha. Yes. Haha. And Nelson. Makes sense. Okay. So we're going to move on to how can we solve a logarithmic equation. So we're going to have 3 different methods for ways that we go about this. All right, the first method will be, I don't think you guys can see that fully. Hold on, let me shift this over. It was just a parentheses, but still. Okay, first method. If the equation is just log equals log, okay, this is what we're looking for in order for it to be a method 1 equation. Right, so what do? Well, then as it says, we just drop the logs and set the stuff inside equal to one another and solve it. So let's take an example. So before I talk about method 2 and method 3, let's just take a look at that. What does that look like? All right, so that would be this first example right here. Log base 9 of 3x minus 5 equals log base 9 of 15. Okay. I'm immediately seeing that on either side of the equation, I just have log base 9 equals log base 9. There's nothing else. Okay, there's stuff inside the logarithms. That's fine, whatever. But there's nothing else on the outside. There's no like plus stuff on the outside, or there's not more logarithms. It's just log equals log. All right. So this is a method 1 equation. Well, so what we can do, I wrote that behind my head, sorry. What we can do is then say, great, well then who cares about those logs? Let's just look at this stuff that's on the inside. Set that equal to one another, and we can just solve this. And this is easy. This is just a basic 2-step equation. Add 5 to both sides. Divide by 3. X equals 20/3. Let me write up another quick example here just to demonstrate. Question. Yes, hit me with the question. Whew, it is raining out there. Oh my gosh. Do the logs have to be the same? Yes. Great question. Well, if I understand what you mean. This is base 9 and base 9. So yes, the base of the logarithm has to be the same. It would have to be log base 9 equals log base 9. Or log base 12 equals log base 12. Or natural log equals natural log. Is that what you're asking? So yes, the bases have to be the same on both sides. Okay, yeah. Exactly. All right, so same thing on this second one that I drew. I have log base 4 equals log base 4. There's no other stuff on the outsides of those logarithms. It's just log base 4 equals log base 4. So let's take this stuff on the inside and set it equal. So 3x equals 2 minus 5x. Just forget the logs altogether. Add 5x to both sides. 8x equals 2. Divide both sides by 8. X equals 2/8. Of course, if we can simplify a fraction, we want to do it. So we'll go one step further and simplify this to 1/4. That's method 1. And it's kind of the most simple version that we have. Very similar to our exponential equations, where if I had something like this, and we said, hey, the bases are the same. It's a 2 on both sides. So whenever that was true, then we just looked at the exponents. We just said, okay, forget the bases of the exponentials. Let's just set these exponents equal to one another. Right? Basically the same type of thing here. If we see log base 4 equals log base 4, the bases are the same, okay, then great. Forget that stuff. Just set the inside stuff equal to each other. Right? So very analogous to one another, whether we're talking about exponentials or logarithms. Okay, so let's go back one slide so that then we can go forward. So that was method 1. Now method 2, so how do I know if I'm using a method 2 equation? Right, well, yeah, that's fine. So a method 2 equation only has log on one side. Okay, so there is not a logarithm equals a logarithm. It is just on one side of the equation, there's logarithm and maybe some other stuff besides the logarithm. On the other side of the equation, there's just some sort of stuff. Okay, but it is not a log equals log. There's one logarithm somewhere in the equation, but it's only on one side. Okay, so if that happens, we'll use exponential to solve it. This was out of order, so let me go to this. Actually, let me do this one. So I had to skip a slide. Sorry, mine are slightly out of order. Let's go to this example. So again, I'm seeing I have one logarithm. Now on the left side, there's more stuff. There's a times 3, there's plus -5. On the right side, there's just 13. But the point is, there's only one logarithm on one side. Method 2. No, not quite. Mr. Abundance, try again. Method 2. Okay, so method 2 is going to be, let's use exponentials. Okay, but my first step is going to be to isolate the logarithm. Right, so that whole thing that I just highlighted, I want to get that by itself. So the -5 and the +3, I want to get rid of those. I want to move them to the other side. So let's start off by first adding 5 to both sides. So 3 log base 2, 7x plus 1 equals 18. Now I need to get rid of this 3. So let's divide 3 on both sides. So log base 2 of 7x plus 1. 18 divided by 3 is 6. So that's fine. That's solving that we've normally done. But now here's where it gets a little different into something we haven't done before, is how do I get rid of this logarithm? Well, we know the inverse of logarithms is exponential. So we're going to use an exponential. And specifically, since this is a base 2 logarithm, I'm going to use a base 2 exponential. But what does that mean? So what that means is I'm going to put a 2 on both sides of the equation. And now everything that originally was part of the equation, I'm going to move that up. I'm going to bump that up into an exponent. So log base 2 of 7x plus 1 gets bumped up into the exponent. And then on the right side, we had the 6, so the 6 gets bumped up into an exponent. Okay, so that's kind of the new step that we haven't seen before. If that doesn't make sense, that's fine. Just ask. It's kind of weird. Right, but again, so everything that was originally in the equation gets moved up into the exponent. Now that we have an exponential base 2 and a logarithm base 2, those cancel each other out because they're inverses. So now on the left side, all that we have is 7x plus 1. And on the right side, I have 2 to the 6th, which is 64. Yeah, right? I think so. Right, 2 to the 6th power, 64. And now we just have a basic two-step equation. We'll subtract 1. 7x equals 63. Divide by 7. X equals 9. That's a method 2 if we just see one logarithm. So here's another example of that. Again, this is the only logarithm I see in the problem. Right? There's other stuff outside of it, and on the right side there's other stuff, but there's only just one singular logarithm on one side. So I can identify this as a method 2 equation. Now, do you need to memorize like which method is which, like method 1, method 2, method 3? No. I'm never going to ask you like, what is method 2? All right, but I just need you to know if you see just one single logarithm on one side, then that you know the steps you should do. I don't care that they're actually, the official name of these isn't method 1, method 2, method 3. I'm just numbering them this so that we can kind of keep track of them better. But whatever. All right, first I need to get rid of that negative 4 that's being multiplied. So I'm going to divide it on both sides. Plus 2x. Negative 16 divided by negative 4 is 4. All right, so I've isolated the logarithm. Now, since I see that the base of the logarithm is 3, then I'm going to choose to make an exponential of base 3. It has to be the same as the logarithm. So I'm going to put a 3 on both sides. Right? And this, come on, give me red. All this stuff that was originally just my equation is now going to get moved up into exponents. So log base 3 of 5 plus 2x equals 3 to the power of 4. On the left side, 3 to the power of log base 3 cancels. So 5 plus 2x equals 3 to the 4th. 3 squared times 3 squared, 9 times 9, 81. Now we have a much more manageable equation to work with, just a two-step equation. 5 plus 2x equals 81. So we subtract. Subtract 5 on both sides. 76. Divide both sides by 2. 38. X equals 38. And so that's method 2. Use exponential. What is it? 1201? Okay, that didn't take as long as I thought it would. What do you think? We could power through and finish method 3 today as well, or we could just stop here and then talk about method 3 tomorrow, finish it up tomorrow. What are the dogs' thoughts? Mocha votes for finish method 3. Shada didn't have a dog, so just Shada votes for finish method 3. Well, Shada might have a dog, but Shada didn't tell me at least that there was a dog with her at this time. Where's Aiden, the official spokesperson? Okay, well, I guess we're finishing method 3. It won't take too long. So let's go back. Method 3 ooh, that's gross. Let's use yellow. Okay, method 3 is if the equation has multiple logarithms. All right, so method 1 is there's 2 logarithms, just one on each side, and that's it. Method 2, there's 1 log on one side, and that's it. Method 3 is I see that there's multiple plus some other stuff. Okay. If this happens, we're going to use our log properties, so like we did for expanding and condensing, to make it look like either method 1 or method 2. Either way. Okay, so here's an example of what that would look like. So I have 1, 2, 3 logarithms. This is not method 1 because method 1 is just log equals log. But this is log minus log equals log. All right? It's different. 3 different logs. So I want to use my properties to try to make this look like method 1 or maybe method 2. So what I'm most intrigued about when I look at this is that there is this minus sign in between the 2 logarithms. And these logarithms are the same base. So that tells me I can use my properties to condense these together. And whenever there's subtraction between 2 logarithms, I know that we can combine that as division. Log base 4 of 5 cubed. I'll go ahead and calculate. 5 cubed is 125, so I'll go ahead and just put 125 in here. Will we have a performance task over any of the stuff we have learned so far? Yes, I'll talk more about that after I'm done with this. Okay. So now I've done exactly what I wanted to do. This now looks like method 1. Just log base 4 equals log base 4. So great. Let's look at just the stuff on the inside and set that equal to each other. 12 over 5x equals 125. And we solve. So multiply 5x on both sides. So 12 equals 625 times x. And then divide both sides by 12. 12/625. Okay, so that's using the properties. Typically what that means is if I start off with two logarithms on one side and they're being added or subtracted together, well, if they're being subtracted, combine the two logarithms so that they're in one logarithm being divided. If it's addition between the two logarithms, then combine them so that they are being multiplied inside the logarithm. So there's my methods. Okay, so back to E-Waller 123, which could be anybody. All right, I have no idea. Will we have a performance task? Yes, we will have a performance task. It will look different than a typical performance task, but it'll still be. So when I guess it's kind of vague when you say any of the stuff we have learned so far, like in terms of while we've been on virtual learning. So like the exponentials and the logarithm stuff. So like, but yes, we will have one that is over exponentials, like the exponential growth and decay problems that we did at the beginning, or like at the beginning of coming back from break. And we'll be over some logarithm stuff, and more specifically, the logarithm word problems that we get to on Monday. Okay, and so we still have a few days. We'll probably get that on like Wednesday is when I'll give that to you. And I'll kind of explain more, but it won't look like a normal performance task. It'll be much shorter. Okay, maybe anywhere from like 2 to 4 questions. And there'll be an emphasis on problems where I ask you to explain things. So you guys have had a couple performance tasks from me. You know that I like to give like a question, at least one question per performance task that's like, explain the reasoning behind why this thing happens. Or, on one of the performance tasks, it was like, are these two graphs inverses of one another? Explain why or why not. So that it's not just, do you know the rule, or not just, do you know how to solve it, but can you explain why? And can you show me that you understand why these steps are being taken? If that makes sense. Because obviously I can't like monitor you guys, or I don't know, I'm not going to like make you get in a Zoom conference and be watching you on Dyno while you take a performance task or whatever. So so the emphasis, the shift will be more on not only can you solve something, but do you actually understand what's happening, and can you explain to me whatever question I ask you about it? Hopefully that was coherent. Coolio. Yeah, I mean, I guess you could listen to the rapper Coolio while you're doing the performance task. That's fine. It's kind of very old school of you, very 90s, but Coolio had some good hits, so that's fine. So yeah, probably look for that around Wednesday. Will it be similar to the vacation worksheet where we email you our work? Yes. Yeah, that's my plan. Unless you have a better option. I guess, I don't know. I thought of like just doing kind of like a normal, in other classes you can access the actual documents or whatever through Summit. So like maybe if I put it on Summit so that you had your own copy, and then for the explanation part you could just type whatever your explanation is, and then for the math part you could just like insert pictures of your actual math. I don't know. Do you think that would be better? Or do you like just taking pictures and emailing? Because again, I want to do whatever's easiest. I don't want to make more problems for you guys and just more work. Fine with emailing it. Okay. Email. Okay. Yeah, I think that's pretty easy. But I mean, if so, let's say alternatively, if that's something that you want to do, like if you don't want to write explanations out, if you could just, if you wanted to make your own Google Doc and type the answers to the explanations that you want to type and then insert pictures and then just share that Google Doc with me, you could do that as well. Do you think we will actually return